Okay, so this is the final video in our series on non-parametric tests. The purpose really is to mop up a few issues I felt that might come up having listened back to the previous videos. It might be nice to look at a comparison between the signed test and the signed rank test. I have mentioned that this one tends to be more powerful. In a sense, it's more likely to pick up a rejection of H0 when it should be rejected. So I just want to, through this use of a simple example, look at that. Through that same example, we'll look at where these critical values are coming from, that come from the tables. And then we might do something similar for the Wilcoxon Ranksum test as well. We should come on to that. Okay, so here's a starting problem, simple problem with just 6 data values under this hypothesis. You might want to pause the tape now and check you can do these. Okay. Right, so let's have a look at the sign test first. Sign test just looks for the number that are above or below the median under the null hypothesis. So we could let x be the number above median. And in this case, so we've got x is binomial 6, 0.5, assuming the null hypothesis. And we've got 1 only that's above the median, the presumed median, which is 30. So we test x being 1 or something even more surprising than only 1, none. Those two together, and we can get those numbers from the tables. Hopefully you're used to that now, so I'll just write the number down. 0.109. So we reject the null hypothesis. No, we don't. We do not reject the null hypothesis because it's greater than 10%. So we do not reject H0. And then we come up with the contextual statement. Insufficient evidence and context. There isn't any here, so we'll just move on from there, but always remember to give context. Okay, so that's the first bit. The first one was do not reject H0. Okay, let's now look at the Wilcoxon under the set with the same data. Right, with the Wilcoxon, let's write out the data again. So we find the differences from the median. Or the presumed median under the null hypothesis, which is 27. So that's minus 10. This is minus 8. That's minus 7, minus 4, minus 2, and positive 3. And then we rank them. We rank them in terms of the moduluses of those. So obviously the smallest there is 1. The next smallest is the 3. The next smallest is the minus 4. Like this. Okay, and then we actually, what we do then is talk up the signed rank, which is the negative of the rank taken into account whether it was above or below the median. So this one is, all these were below. And this one was above, so that's 2. So our W plus, which is clearly the one we need to look at here, is equal to 2. W minus is equal to minus 6, minus 5, minus 4, minus 3, minus 1. Clearly not the one we need to be considering, which is 19. And something I didn't mention when we came in this first time round, I probably would, on reflection, do a check to check that these actually add up to n, because we should always have W plus W minus adding to the total of the ranks, because 1 plus 2 plus 3 is the triangle numbers basically, or the counted numbers. Using that, so it's worth checking that they do add up to 21, and they do. because that's 6 times 7 over divided by 2, which is 21. So it's all good. But obviously the critical value here is 2, which is, let's look in the tables. 2 is just about, it is passing, but it does qualify, if you like, for rejection of H0, because it just about gets there. So in this case, because it's a 5% test one tail, we reject H0, and there is sufficient evidence and so on. Okay, context, there isn't any context here, but even then you'd say there is sufficient evidence to suggest that the median is reduced or less than 27. Okay, so just the reason why we've done this example is because we have an example where the two tests have come to a different outcome. And why is that? And basically, as I've mentioned a number of times now, the signed rank test, if we can assume symmetry, that's important, is the preferred option, because it takes account to how far the remaining number is from the median. So for example, this 30 here that we had here, for that number was the one number that was above the median. With the sign test, it wouldn't have made any difference if that number were 28 or 48 or 108. It would have given the same answer. Okay, whereas with this test, obviously, if the number was 108, for example, then that's a long way from the median, which would affect our rankings quite considerably. And this number, which we had as 2, would have actually then ended up at 6, which would have failed the test. So in fact, if our number had been, because 23 is the next closest to the median, if our number had been 34 even, okay, then we are already, that our ranking here would have then been 3 rather than 2, and we would not be rejecting H0. So it's more powerful. It's taking account of how far numbers are from the median. Okay. On the other hand, if the number was even closer to if the number was even closer to the median, say 28, then this number would have become 1, and we'd have had even more stronger evidence to reject H0, because our value for W plus would have been 1. But as I say, if this final number here would have been 40 or 45, or say, I'm not sure where the boundary is, this chip thing. In fact, looking at these numbers again, if I'd replace that number here by 32, for example, so only 2 more, then my differences here these differences would have been the same, minus 10, minus 8, minus 7, minus 4. This number here would be 2, and this number here would be, minus 2, and this number here would have been 5. Then the rankings would have been different. So the ranking here would have been 1, 2, and this already then goes to 3, and 4, 5, and 6. So the signed rank would be obviously minus 6, minus 8, minus 6, minus 5, minus 4, minus 2, minus 1, and 3. And so our W plus would be equal to 3, which wouldn't have got us over the line for even at a 10% level, for that matter. We needed to, oh sorry, that's not true. It would have got over, that's a two-tailed test, which is the same. We don't have the values for 10% significance here, but it wouldn't have got us over the line for rejecting H0, just if that final number had been 2 more. So the rank test, the signed rank test actually picks that kind of detail up, whereas the signed the basic sign to test using a binomial does not. It wouldn't have made any difference if the number was 400. For that, obviously, it would be silly to do such a test in those circumstances, but hopefully you've got the idea. So yeah, but it does require symmetry. Okay, that's important. This does require symmetry. So signed rank test is more powerful, but it does require symmetry because it picks up how far numbers are from the median. Okay, so that's the first thing that we've covered. Hopefully we got that comparison. We can see the comparison of that. I want to look at in detail now about where these critical numbers come from. So why was 2 considered critical and 3 not in our hypothesis test here? So now I want to actually look at where these numbers come from. In other words, why is 2 considered critical, the critical value? Why is it 2? Well, I suppose put in another way, what would we do if we didn't have the tables? And of course we could use a normal distribution approximation, but that only gets better when n gets larger anyway. So what would we do if we didn't have these tables? And so where do these numbers come from? Okay, to start this, I'm going to use this example. In other words, we want n, suppose we've got n equals 6. So the non-signed ranks, if you like, the ranks are 1, 2, 3, 4, 5 and 6. Okay, so those are our ranks. So what we could do is W plus is the sum of ranks above median, basically. So I'm going to look at what the possibilities for W plus are. For those of you who have the AI Hodder textbook, this is equivalent to what they're doing on page 290, but I'm actually doing the opposite. I'm going to consider W plus because it's arbitrary and it goes with the example that we've actually done. So we're going to actually look at what W plus could be and look at consider what the W plus value would be there, and just basically in some combinatorics, counting basically, and anyone who's used to this kind of field or mathematics in general, we do like to deal with simple cases. So using n equals 6, I would go even less, but of course our first row has only got 6, so that seems to make sense, and then you can hopefully get the idea going forward from there. So we've got W plus is the sum of the ranks above the median. Basically, we ask the question, what are the possibilities here? And also, more importantly, I suppose, or just as importantly, what will the W plus value be in this case? Okay. Well, we could have basically the empty set, which is no values being above the median, in which case our W plus value would be 0. Okay. We could have 1, in other words, one number above the median, and that being the closest number to the median, in which case the W plus 1 value would be 1, and so on. And we could have the second ranked number from the median being the one higher number than the median. So the number that's higher than the median being the second closest to it, which would give us the value 2. Let's fill in a few more. So this is all the ones where there's only one number which is above the median, but they have a different W plus number because they're all different distances from the median. So for example, with this example here, this would correspond to kind of example, if that were a long way from the median, say 50 or 100, then that would be correspond to this possibility here. Right, so now we can look at the number where two numbers are above the median. So let's just say W plus, we could have the two numbers above the median, but they're the two closest numbers. Okay, so that's would be 3. That would give a W plus number of 3. So yes, they're two numbers above the median, but they're actually very close. They're the two closest numbers to the median. And we can carry on doing all these possibilities, which I'll just list now. So here I've got all the possibilities where there's 2 above the median. There. And I've started to write by hand those that are 3 above the median. In the end, all the possibilities are listed below. Okay, all the way up to 6 possibility, where basically in this case we've got all 6 of them the other way around. All 6 of them are above the median. So this is where the symmetry of the assumption of symmetry is quite important, really, because notice there's a symmetry in the distributions here. So we've got 21 possibilities here and 0 here. There's one way of getting 21 and there's one way of getting 0, and so on. So this here would correspond to W minus being equal to 0. So which is why it was arbitrary whether I chose W plus or W minus. But that's aside, really. What talking about the assumption of symmetry, if we're saying they're equally likely to come, if we're saying the symmetry is in the middle, symmetry in the middle, the median is in the middle because of symmetry, then we can say that each of these possibilities is equally likely. So in other words, any one random choice will have a 50-50 chances of going one side of the median or the other, and that would be the same for 6 chosen samples being above the median or below the median. So on the assumption that they're equally likely to be either side of the median, which it will be if we're assuming the null hypothesis and we're assuming symmetry of the distribution, each of these will be equally likely. Now you'll notice there's 64 of them. Okay, there's 64 possibilities as a whole. Now we could start listing all the different ones where we can get, how can we get W plus is equal to 0? Well, there's only one way of getting that, isn't there? W plus equals to 0. There's only this one possibility. So that gives as a probability of 1 over 64. The probability of W plus being equal to 1 there's only one way of getting that, which would also have probability of 1 over 64. And similarly, the probability of W plus being equal to 2 would again be 1 over 64, because there's only one way of getting 2. The probability of W plus being equal to 3 has got, actually there's 2 ways of getting that, because we can have a 3 and we can get in that way or that way, so that would be 2 out of 64. Okay, so looking back at our values, we can say the probability that W plus equals to 0 is equal to 1 over 64. The probability that W plus is less than or equal to 1, which would be the critical value, would be corresponding to a critical value of 1, would be 2 times 1 over 64, 1 over 64 plus 1 over 64, which is 1 over 32, which is 0.03125. The probability of W plus being less than or equal to 2, again, would be 1 out of 64 plus 1 out of 64 plus 1 out of 64, so 3 out of 64, which is 0.046875. And finally, the probability of W plus being less than or equal to 5, because there's two ways of getting 2 out of 64. That would be 5 out of 64. And that equals to 0.078125. Okay, so that means, because this is less than 5%, and this is greater than 5%, that demonstrates why the critical value of 2 does get us over the line for a 5% one-tailed test or a 10% two-tailed test, because it's less than 5%. The probability of W plus being less than or equal to 2 is equal to 0.46875, which is less than 5%. So that number corresponds to that, because it's just about getting under the boundary, because the next one doesn't. Had we had an extra column there with a one-tailed test of 10%, then 3 would have been included in it. So in other words, if we had a 10% at one-tailed, 3 would be the critical value there, because this is less than 10%. Okay, so that's the way it works. Let's imagine that our test was 1% though. If I had 1% significance level, well, actually, not even 0 would not even 0 catches that, which is why this is blank. Because even if you get 0, okay, 1 divided by 64 is equal to 0. Which is less than 1%. It's 0.015625. So that 0 doesn't even qualify for a 1%, because the sample size is too small, but it would do for a 2.5%, because it is less than 2.5%, but 1 doesn't, because that's 3%. So 2.5% or 5% two-tail, you need 0, because this is less than 2. This here is less than 2.5%, but it is, but this bit here is greater than 2.5%. So which is why we need to have 0 for a 2.5% significance level, rather than or a 5% two-tailed test. Okay, and just to say again, obviously it's arbitrary. Had we gone the other side, here the W minus numbers would be the smaller ones, obviously, given the fact that they both add up to 21. So you have that symmetry there. Okay, now let's look finally and briefly, because it's going on a little bit, at the critical values for the Wilcoxon Ranksum test. Now turning to looking at where the critical values for the Wilcoxon Ranksum test. Remember, we're comparing two different sets, M and N, where M is the smaller value. Again, going to do this by example rather than try and generalize. Let's just look at a relatively simple example, 4 by 5. Okay, and we can see the critical values that we have for 4 by 5 are 12, 11 and 10. So that should enable us to actually see by actually looking at probabilities, we should see why those numbers come to 12, 11, 10. So remember, we rank numbers, so we're going to have 9 possible rankings here, and they could be assigned to each group, but there's going to have 9, we're going to have 9 numbers in the ranking. So the possible different arrangements of 4, let's just consider what the possibility is for getting an RM value. So if all of the smaller numbers are smaller group of 4, so that's the smallest RM value we can get. So if all of the smaller rankings are in the group of 4, then we'd have an RM value of that corresponds to 10. Okay, If, on the other hand, we can get an RM value of 11 also by having all of them but one in the group of 4, so that, in other words, the fourth smallest number is in the other group, but every others in the group of 4 is smaller, will give us an RM value of 10. Now, if we had all of the first 3 smallest in the group of 4, but then the next 2 smallest in the other group, and then the next smallest in the group of 4, we'd get 1, 2, 3, 6, which would give us an RM value of 12. But that is not the only way of getting 12. We can also get that by having this arrangement, the first 2 being in the smaller group, the next one being in the other group, then the next one being in the smaller group, and the next one again being in a smaller group, like that. Both of those give us an RM value of 12. Now we can also list the number that gives us an RM value of 13, and we can see that there's just 3 of them. So those, I'm just going that far because that's as far as the critical values that we're looking for, and one more. So we should find that this one goes above the threshold for rejecting H0, and these do variously at different significance levels actually go far beyond the threshold for rejecting H0. Okay, so first thing to note is that these, basically what we're doing is we're choosing 4 numbers. Right? Imagine these were equally likely, because these can be any numbers from the set 1 to 9, and they're chosen randomly. If they were equally likely, then the number of possibilities, because you're basically choosing 4 numbers from 9, so it's 9 choose 4, 9C4, which is equal to 126. So if it were all random, they would all be equally likely. So if each one of these particular ones, if they were randomly chosen to be, because remember we're saying if they're from the same distribution, then it's just random whether they end up in one group or the other, so they got an equal chance, which means that each one of these has an equal possibility if they come from the same distribution. So just to remind us, just in case you forgot what we're trying to do, we're trying to justify these critical values in this particular case for a 4 by 5, and we've worked out some possibilities where the RM number is small, and we've gone between 10 and 13 to try and justify why these numbers 12, 11, 10 occur. So you can find the probability that RM is less than or equal to 10. I know it can't be less than 10, but just for consistency, but that means the same, it's equal to 10. And again, we're looking at equal likelihood, because if they're from the same distribution, then it's just random whether they end up in one group or the other. So the only reason why it's unlikely to get in, that's unlikely, is because it's the only one way of getting 10. So it's 1 over 126, which is equal to 0.00794. And the key thing here is that is less than 1%. Now let's look at the probability that RM is less than or equal to 11, in other words 10 or 11. There's 2 ways of getting that. So that's 2 out of 126, and that equals to 0.0158. And the thing here is that it is greater than 1%, but less than 2.5%, and less than 5%. Okay, let's look at the probability that RM is less than or equal to 12, so that's 10, 11 or 12, we can see that there's 4 possibilities there. So that's 4 out of 126. So that equals to 0.03175. And the thing here is that that is greater than 1%. It's also greater than 2.5%, but it is less than 5%. Okay, and finally one more. Probability that RM is less than 13. Now the ways of getting 13, now that's all of these possibilities here. So that's 7 possibilities out of 126. That equals to 0.05556. Apologies if I've made rounding errors with these, but hopefully I haven't, and hopefully if you have, you've still got the idea. And that is greater than 5%. So here we go. Let's just summarize what we've got. We're seeking to justify why 10 is the critical value at 1% level. Well, put simply, 10 lies, but the probability of getting 10 or below, it's actually equal to 10, lies below 1%, but the probability of getting 11 is above 1% or less, is above 1%. So 10 is the critical value, because 10 we reject H0, whereas 11 we don't. And similarly for 11 and 12, looking at 11, why 11 is a critical value at 2.5% or 5% for a two-tailed test. Well, it falls below 2.5% for 11, but if it goes above 2.5% for 12. So it needs to be 11 or less. The 11 is basically the largest it can be, because 12, it goes above the 2.5%. So that's why 11 is the critical value for a 2.5% one-tailed or 5% two-tailed. And then finally, 12 is the critical value at 5% or 10% two-tailed, because it's below 5%. So 12 is good enough to reject H0, but 13 is not, because that's above 5%. Okay, so 12 is the critical value, because 12 is good enough to reject H0, but 13 is not. I'll put it in a different way. 12 is the largest it can be in order to reject H0 at the 5% level. So that's it, folks. The end of this video, which has gone on a little bit longer than I had intended, and also the series, which has also gone on a bit longer. If there are any comments or corrections, indeed, because I do make errors, it's not easy sometimes, please do comment below, and if you find them useful, then like and subscribe. That's it for now. Bye.